Hi, my name is Brian Lowe. I'm with Belleson and we make voltage regulators. I'm here to talk with you about measuring power supply rejection, also known as ripple rejection. So I'm going to try and keep this short so that you can get the most benefit out of it in the least amount of time. First, I'm going to start with a quick tour of the workbench and the equipment that we're using to make these measurements. Then I'll show you the measurements themselves. They're on the computer screen, and then we'll do some quick comparative measurements while you can watch on the computer screen of some voltage regulators that we have here as samples. So first, let me give you the quick tour. So hold on. Okay, I'm behind the camera now. That's why here we are looking at the workbench. I'm going to back up on the zoom. We've got a piece of homebrew equipment. I can show you the schematic for that in just a second, and that is being used to send an input signal to the regulator, which is a DC signal with a controlled, specified AC sine wave superimposed on top of it. I've got a voltmeter here that's showing the output of the voltage regulator. This is the one that we're testing currently. It's a Belleson SPZ78 set to 12 volts. We also have a homebrew power supply, which is your basic power supply with a toroid and a toroid transformer, a bridge rectifier, some filter capacitance, and a couple of Belleson regulators. I say a couple, there's a plus and a minus, and they're set up to be adjustable here. We've got 10-turn pots that let us adjust them fairly closely to what we want. And then, so that's the DC going in, and then superimposed on that is an AC coming out of this HP200 CD. This is a nice, long time used and manufactured signal generator, audio signal generator from HP. It goes from essentially 0 to 600 kilohertz, and we're only using the lower portion of that. But the nice thing about it is it's got a differential signal here that's isolated from system ground, so that we can put this in without having to be concerned about the 60 hertz that shows up when we actually connect the ground to the lower side of the signal. Moving further, if we look at here's the schematic for the apparatus, the little homebrew piece that we're generating the signal with. So this is the yellow DC supply, and this is the HP generator. So the DC supply is coming in and essentially using a Zener and a resistor to bias a MOSFET, which is then driving the signal to the regulator. So this is the regulator input. So we've got DC, and then we're superimposing an AC on top of that. We've got a voltage drop from here to here. So we're putting 22 volts in. We're getting 15 volts plus and minus a half a volt of AC sine wave going into the voltage regulator. And with that, we're looking at the output of the voltage regulator with a handy scope, which if you've seen our noise video, then noise measurement video, then you heard what good things I have to say about the handy scope. It's a very nice piece of equipment for a relatively modest cost. It has 2 inputs and a signal generator output that we're not using because of the ground issue that I just mentioned. Also because we're measuring such low values that if I turn this signal generator on, it actually self-couples internal to the instrument over to the scope inputs and distorts what we're trying to measure. So that's why we have 2 completely isolated pieces of equipment, one to measure and one to generate. Actually 2 to generate, one with DC and one with AC. So the output from the handy scope we can see here on the video screen. The top trace is the DC output of the regulator, and believe it or not, there's some signal in there, but it's mostly DC, as you can tell. And then the lower trace is the fast Fourier transformer, FFT, of the upper trace. So this is the frequency spectrum, in other words. So it's really a spectrum analyzer in this case. And you can see, if you look closely at the y-axis over here, we're going from 0 dBV, so this 0 dB is 1 volt, and then down from there, such that minus 120 dB would be 1 microvolt. So we're literally measuring in the range of microvolts one of the nice things about the handy scope is it has a 16-bit mode, and it also has an adjustable input range. If you look up here, you can change the range of the. It's just like the knob on the oscilloscope where you take the range down. Now the lowest range is 50 millivolts, but with 50 millivolts and a 16-bit digitizer, then we can get a very nice measurement of a low frequency signal. I'm sorry, a low amplitude signal. So in this case, you can see that we're generating 1 kilohertz signal. I'm going to take a quick peek. I'm going to go back over to the device under test, and I'm going to hook to the input signal coming from that HP generator. So we'll take a look. Sorry about the jiggly camera. We'll take a look at that with the handy scope, and we'll be able to see that, in fact, yes, there is a signal coming in. Here it is on at a fairly high resolution, so you can actually see the digital steps that are being taken with the digitizer. And then you can also see, I don't know if you noticed the peak value of this before, but it was below this cursor line before, and now it's above. So you can see that, in fact, coupling a signal to one input, which is the regulator output, but coupling the signal from the regulator input, which has the AC on it, actually couples through inside the instrument itself and increases the measurement value that we're looking at. So if I just go and disconnect, let's see, that would be channel 1. So if I go and disconnect channel 1, before I do that, I'm going to put this camera over here, and you can see that 1 kilohertz signal. I'm going to disconnect channel 1, and you can see as this thing averages that signal is dropping. So we're measuring a signal that's so low that the internal coupling of the oscilloscope itself from one channel to the other is affecting the measurement. So we have to be very, very careful. And in fact, I have these 50 ohm terminators that I often stick onto the other channel if I'm not using it, so that we don't end up causing interference from channel to channel. So that essentially grounds that channel's input. So at any rate, you can see that the AC signal coming here is out of the regulator is, at this point, if I look at this is the bottom cursor. So if you see, there's a cursor here, and there's a cursor here, this white line up here. So that's the top cursor, so I could put that at minus 17.5 dB. And then if I look up here, so I didn't hit it exactly, but you can see, hopefully you can see that it says minus 17.28 dBV. The number that we're looking at 1 kilohertz for the feed through, the ripple, is at minus 110.5 dBV, which is right there. So you can see that literally the regulator is pulling everything to almost down to a microvolt of excursion. And if you look at the output signal of the regulator here, that's why it looks so much like DC, because it doesn't even show up at a scale of 50 millivolts per division. However, when we look at it on the spectrum analysis, we can clearly see that there's a spike there. And in fact, if I disconnect, I'm just going to unplug this right here. We'll go back and take a quick look, and we'll watch this. Because it's got an average of 8 full FFT cycles, it takes it 8 times to show what's really happening. But you can see that 1 kilohertz signal disappears to nothing. Well, not nothing, but disappears down into the noise, which is below a microvolt. 1 microvolt would be at this point right here, this horizontal axis line, and so at 1 kilohertz, the noise coming out of the regulator is actually below a microvolt. But the ripple that gets through is, again, I'll put this put the AC back in, and you can just watch that signal grow back up as it takes additional samples. So these samples are doing a rolling average, so that's why it takes a little time for it to stabilize. Now what we can do is get a comparison check. I'm going to set up the tripod here so that this will be a lot simpler and you won't have to watch the camera jiggle so much. Okay, here we are. I've replaced the SPZ78 at 12 volts with a TPS-a.k.a. 4700 that's been set up to deliver roughly 12 volts, or nominally 12 volts. And also we've got the same 1 kilohertz signal going in. I'm standing out of view of the camera, but you'll be able to see me wave my hands around. So you can see at 1 kilohertz, this cursor is still set where it was with the SPZ78, and you can see that the value of the ripple getting through the regulator is higher in this case. Now it's not terrible. It's pretty darn good for a monolithic regulator. Let's see, we are at this point roughly 10 dB more of ripple rejection, 10 dBV, so that's a little more than double the ripple that's coming through at 1 kilohertz. Alright, and I noticed that I'm over 10 minutes already, so I'm going to try and speed this up a little bit. I'm going to put in some others and tell you what they are and give you a quick look. Alright, now we're looking at an LT1085 high current regulator. You can notice right off that the noise is higher because, in this case, the cursor hasn't moved. That's at minus 110 dB, but you can barely see it because the noise level is actually obscuring it, and so the noise of this part is at roughly the same point that the rejection of the SPZ78 is. So if I pull this cursor down, we're looking now at minus 83 dBV. So for this monolithic regulator, it's got significantly more ripple at 1 kilohertz than certainly than the SPZ78, but also significantly more than what you would see in the TPS-a.k.a. 4700. Now you're looking at the LT3080, which that's a really good monolithic regulator that Bob Dobkin designed and that won a number of awards a few years ago. And you can see that the noise on this regulator is nice and low, is very nice and low. If you look here, you can see that that there's some 60 hertz showing up in our measurement that's coming through at about, I don't know, minus 100 dB or so. And the ripple that's getting through is minus 97.5 dB roughly, which is good for a monolithic regulator. It's still, you know, maybe 13 dB worse than 12 dB worse than the SPZ78, but significantly better than the TPS-a.k.a. 4700, and way better than the LT1085. All right. Okay, just real quick before we get to the LM317, I wanted to give you a view of what's set up for the LT3080, and the LM317 is very similar. I can't seem to get this to focus right, but at any rate, you can see that it's kind of got a bunch of stuff hung on it. Since these are adjustable regulators, they need resistors to set their value, and there's also on this one there are 2 capacitors on it to stabilize the output. So it's not just that we're plugging in a regulator in some cases, because there needs to be additional circuitry in order to get the voltage that we're looking for and that sort of thing. So we've done this with the LM317 and the LT3080. So now we've got, if you notice here, we've got the LM317, the one that has been around for so long, and it's been a workhorse for years and years. You can see that there's a fair amount of ripple coming through, and the value of it at this point is, for this particular unit, is minus 82 dBV. So you can see that's significantly worse than anything we've looked at, with the exception of the... Okay, now you're looking at another small boutique manufacturer of voltage regulators. This is from Sparkos Labs, and I have to say, from my experience and my measurements, it's a very good regulator. And the ripple rejection at 1 kilohertz is just a little bit higher, a little bit worse than the SPZ78. It's at minus 106 dB, where the SPZ78 was at minus 110. So it's really a nice finally regulator. We finish off with the ubiquitous LM7812, and if you have any equipment with this, you should just go and swap out the regulators with something else right away if you have any concern about the integrity of the supply voltages in your system. If I go and check the number, we're looking at 1 kilohertz, we're looking at minus 73 dBV. So that is significantly worse than anything else we've looked at, including the LM317. It's not horrible, but if you're concerned about noise and ripple rejection and dynamic response and other things, then this is not a regulator that you want in a high performance system. As a final tease, I want to show you, this looks like just a noise spectrum because there's nothing showing at 1 kilohertz for ripple. However, there is actually a part in the socket, and it's the latest and coolest and greatest new regulator that's coming from Belleson before the end of this year, 2018. Put myself in the picture. So I just wanted to let you know that this is something that has been under development for multiple years, because it's really hard to improve on something that's really good to begin with. And it has taken a huge amount of time and research to be able to come out with this new part, and it's really an improvement in terms of ripple rejection, in terms of output impedance, and in terms of dynamic performance over even the SPZ78. So look for something in your email box sometime this fall, and we'll be announcing it soon. And I hope you also, if you have a chance, will take a look at our noise measurement video. And also we have a video coming soon to show output impedance. So thanks very much for watching. This is Belleson. If you have any questions, feel free to send an email to super@belleson.com, BELLESON.com, and we'll answer your questions. And good luck with your projects and with your audio electronics. Thanks a lot.